Welcome to BYJU'S Exam Prep, India's largest exam preparation platform. So, yesterday I have done a session on how to prepare for communication, what books to follow, and what is the process to prepare communication efficiently, right? So, if you have not watched the session, if you wish to know that, you can watch yesterday's session, right? And in today's session and in the next 8 days also, I will be taking each day one concept. And I'll be discussing it in detail. Whatever concept I'm going to discuss, I'll be discussing in detail, the way I discuss in paid classes. And so today's session is on PCM. Yeah, pulse code modulation. And tomorrow I'll take a session on whatever concept we have discussed today. We will solve all the possible questions in tomorrow's session. Okay. And in next session, after day after tomorrow session will be differential pulse code modulation, and after that I'll discuss delta modulation, and after that again problem session. Similarly, I'll discuss few more concepts. Okay, right. So don't miss the classes. The way I discuss in paid classes, the same way I'm going to discuss here in deep. Generally in YouTube sessions we'll not get time to discuss everything in detail, but here I'm picking each concept and I'm trying to discuss in detail. Okay, fine. So we'll start with the session. So before starting the session, let me just give my introduction. So I've done my master's from IIT Madras with specialization communication systems, and my area of expert is also the same thing, communication systems and signals and systems. So I used to work for the topmost institutes in the country for the last 10 years. So these are the institutes I worked for, and this is my Telegram group. If you wish to ask me any questions based on the subjects or anything else that you wish to ask me, you can contact me in this group. Right. So let us start the session. Right. So before starting pulse code modulation, let's understand what we are talking about. Okay, So we are talking about analog to digital conversion techniques. Okay, the different types of analog to digital conversion techniques that we use in communications. For storage, it's a different story. So you can convert an analog signal to digital signal for storage purpose. That is one reason for analog to digital conversion, because digital storage is more convenient, more cheaper, right? So for the sake of storage, we can convert an analog signal to digital. And the other reason for analog to digital conversion is for communication. Because digital communication is more advantageous. We are having lots of wonderful advantages with the digital communication. We get wonderful quality, we don't need to spend much power, and we are having many advantages. So because of that, we wish to use digital communication than analog communication. But the basic signals like voice, audio, video, these are analog signals. So if we can convert these analog signals, voice, audio, video, to digital signal, then we can take the help of digital communication and get all the advantages of digital communication, right? So the second reason for analog to digital conversion is for better communication. Okay, to get all the advantages of digital communication, we convert analog signal to digital signal. So what are the techniques that we have? So when you're converting analog signal to digital signal, should we be able to convert it efficiently or not? If we are not converting efficiently, what I mean by that is analog signal is converted into huge data. Then this huge data, if you want to transmit, you need huge bandwidth, huge power. Right? So converting an analog signal to digital signal should be done efficiently, which means analog signal should be converted into digital signal. Digital signal means the bits, right? So we should convert an analog signal to bits to least number of bits possible. If you can convert an analog signal into bits, the number of bits that you are using to convert an analog signal to digital, that should be as minimum as possible. It should not be so minimum that you lose quality of the signal. You should not lose information. Without losing information, whatever is the minimum number of bits possible, if you can convert analog signal to digital signal using minimum number of bits, that is what I mean by efficient conversion of analog to digital conversion. Is this efficient conversion required or not? For communication, yes, this efficient conversion is very much required. Okay, because we are shortage of bandwidth. In wireless, especially in wireless communication, wireless bandwidth is of very much shortage. The same bandwidth we have to reuse. In Delhi, whatever bandwidth we are using, same bandwidth we are using in Hyderabad also. Same bandwidth we are using in some other place also. Why we are using the same bandwidth? Same frequencies like 1000 megahertz, like 1 gigahertz, 2 gigahertz frequencies. These frequencies is what we are using for mobile communication. The same frequencies are used in Hyderabad, in every city. Why are we using the same frequencies? Why are we not using some other frequencies? Because we are having shortage of bandwidth that we can use. Sir, there are infinite frequencies to use. Why are you saying there is shortage of bandwidth? Yes, there are infinite frequencies. Yes, I can use 100 terahertz also, but we don't have. There are multiple reasons why we can't use all frequencies for wireless communication. Multiple reasons. One reason is we don't have circuits that can process higher frequencies. Higher means we are capable of communicating signals up to 10 gigahertz, 20 gigahertz, or up to 50 gigahertz also, but not more than 100 gigahertz. More than 100 gigahertz communication wirelessly, we don't have equipment to do that. Right now, we don't have equipment. In future, we might discover and we might be able to communicate with higher frequencies also. Then we'll get more bandwidth. First reason is lack of circuit that can process higher frequencies. Second reason is losses. Wireless medium that we have, our atmosphere, the troposphere, stratosphere, ionosphere, these mediums, they don't allow very high frequency signals to travel long distances because huge losses will be there. So that's why using frequencies higher than 100 gigahertz and all that, it will be very difficult to propagate long distances. So that's why we are having shortage of bandwidth. Since we are having shortage of bandwidth, we can only transmit only certain amount of bits or certain bit rate only we can transmit wirelessly. So why I'm talking about bandwidth is, since bandwidth is of shortage in wireless, we have shortage of bit rate also. We can transmit only up to certain bit rate. Okay. To transmit more, to get bigger higher bit rate, we don't have higher bandwidth, but we are using some other techniques. Like we are using MIMO concept, or we are using a few other concepts to increase bit rate, but not bandwidth. Bandwidth is available, whatever bandwidth is available, that is fixed. Okay, that we are just trying to reuse. If you reuse more number of times, we can get more bit rate. That is one way. But the point I want to make is bandwidth availability is less. Since bandwidth availability is less, bit rate at which we can transmit also, there is a upper limit. So that's why we have to convert analog signal into as less number of bits as possible. So the techniques that we have for this are, PCM is one technique. This is a basic technique which is used to convert an analog signal to digital signal. And the second technique is differential pulse code modulation. This is the second technique. Third one is delta modulation. Fourth one is adaptive delta modulation. So these are the four techniques. There might be some other techniques also, but in our textbooks, these are the general techniques. These are the techniques that are being discussed in our textbooks. Practically, some companies might be using a combination of these techniques or an advanced version of these techniques also, but in our textbooks, we are having these four techniques. Okay. So companies will use their proprietary conversion techniques, which are like improved versions of this also. Right. So what is our target for today? So today our target is the first technique. So we're going to discuss this one today. In today's session, we are going to discuss this technique. Day after tomorrow, I'll discuss this one, and day after that, I'll discuss this one. So these three techniques will be discussed in the next few days. Right. First, let us target the first technique, pulse code modulation. This today whole class is dedicated to pulse code modulation. Right. So this is the block diagram of pulse code modulation. So what blocks do we have? We are having one block: sampler, quantizer, and encoder. I'll discuss it as a whole at the end, but for now, what I'll do is in the next slide, I'll talk about sampler. Sampler is a huge concept. I'll not be able to get into the details of in-depth details of sampler, because generally I take around 5 to 6 hours to complete this topic. So natural sampling, practical sampling, ideal sampling, bandpass sampling. There are multiple sampling techniques. Huge, very wonderful mathematics is also involved there. So I'll not be able to cover sampling topic in today's session because that's a big topic. And this is quantizer. Quantizer is also a big concept. It takes around 3 to 4 hours minimum to cover this concept. But in today's session, I'll discuss whatever basic idea is required to understand quantizer. That I'll discuss. Along with that, when any problem possible on PCM, is a problem based on sampler or quantizer or mix of these blocks. Okay, when they give you questions on PCM, the question can be based on whatever is the output here, that is bits. They can ask about bit rate or bandwidth of the signal here. Okay, or they can give you questions based on, for a PCM system also, PCM system has sampler and quantizer, so they can ask questions based on sampling rate or sampling time or quantization error, SQNR, or based on this block also. I'll deal block by block. Okay, so first let me deal with sampler block. I'll give you the rough idea of sampler, what does it do, and what are the important things that we can understand from sampling. Okay, and what type of questions can be asked from sampler, the basic questions I'll discuss. And after that I'll discuss quantizer, and after that I'll discuss encoder, and after that we'll mix all the blocks and we'll try to generalize what we have understood from PCM system. Okay, so try to understand the concept very well, because it's very important. Every point that I'm going to say is very important. You have to listen very carefully. If you listen very carefully, you don't need to rewatch the video. Otherwise you have to rewatch it multiple times to understand it to the core. Okay, so focus well. Right, wonderful. So the first block is sampler. What does a sampler do? Try to understand. Sir, sampler will do sampling only. Okay, that's fine, that's a simple answer. But let me explain a little bit. Let me say there is a message signal m of t. There is a message signal m of t. Let me draw some shape just for you to understand. Some shape I'm drawing. And m of t is a continuous time signal, or you can say analog signal. And m of t signal, when you do sampling, what happens? Try to understand. In this signal, how many samples are there? At 0 seconds there is one sample, at 0.1 second there is one sample, at 0.2 seconds there is another sample. At every point of time, at every instant of time, we are having one sample. Like that. Within finite amount of time, let's say this is let's say something like 1 second or 2 seconds. Within finite time, and it need not be 1 second or 2 seconds, it can be any finite time. Within finite time, can you tell me how many samples are there here? How many samples are there? There are infinite samples. Because there are infinite instants of time, 0 to 1. How many time instants are there? How many time instants are there? Infinite, right? Because there are infinite time instants, at every instant we are having one sample, so there are infinite samples. There are infinite samples. So now we have a reason to sample. What is that reason? Is it easy to store infinite samples or finite samples? Obviously finite samples only, no? Is it easy to communicate infinite samples or finite samples? Obviously finite samples. So that we got the reason now why we should sample. Why we should sample? Because it's easy to store, it's easy to communicate finite samples than infinite samples. So that's why we want to sample. So if you sample, what are we going to get? If we sample, out of these infinite samples, what is the meaning of sampling? There are infinite samples. From this infinite set, we're going to pick a few samples. We're going to pick only few samples. We're going to pick only few samples, something like this, as a function of time, and we're going to pick at multiples of Ts. T means time, Ts means sampling time. S represents sampling, 4 Ts, 5 Ts, and so on. Out of the infinite samples available, I'm collecting few samples. I'm collecting few samples there. Okay, right. Converting infinite sample signal to finite sample signal is what we call as sampling. So from m of t, we got m of nts. Correct or not? Instead of t, we are having ts, 2ts. A signal exists only at multiples of ts. So instead of that variable t, yes, there is nothing wrong in writing it as t, but exactly speaking, where is it existing? It is, the samples are existing at multiples of Ts. Okay, so what is the sampler doing? It is converting infinite samples. It is converting infinite samples at infinite time instants to finite samples at finite time instants. Correct? So the job of a sampler is to convert infinite samples to finite samples. Okay. Right. So try to understand this. So sampling, we have understood why we are doing sampling and what is meant by sampling. Okay, that is what we have understood till now. Okay, so we have understood what is meant by sampling and why we are sampling. But the real question, or the question based on which questions can be asked, is how to do sampling. That is the real question. We should understand how to sample the signal. So before talking about how to sample the signal, when we are sampling the signal, what care should be taken? What is the care that we should be taking so that we are sampling will maintain the quality? The care should be taken when you are sampling. One thing should be kept in mind. The only thing that should be kept in mind while sampling is, why are we sampling? We are sampling for an advantage. The advantage is easy to storage, easy to communicate. We are having advantages. But we are not going to get those advantages if you are losing the quality of the signal. So we have to sample to convert the signal from infinite samples to finite samples. But in that process, we should not lose the quality of the signal, or we should not lose the shape of the signal. If you lose the shape, there is no point of conversion, right? If you lose the shape, if you can't get it back, then what is the point of doing sampling? If you store the wrong signal, if let's say you have sampled, okay, you have sampled incorrectly, okay, if you are having samples, you have stored it, you retrieved it back. From those samples, if you are not able to get back the original signal, then what is the point of sampling? So we have to sample in such a manner that quality is preserved. This thing should be kept in mind. So the question is how to sample the signal? By preserving the quality. Without preserving the quality, there is no point of sampling, right? So how to sample? By preserving the quality. So you'll understand it better. Okay, you'll understand it better now. Let me give you one more example. I can collect samples like this. Out of infinite, I'm collecting finite, right? So instead of collecting like that, let me collect something like this. Something like this. I've collected from infinite, I've collected finite samples. Is the shape preserved? You can observe that there is the envelope of the signal is preserved here. But if you see the envelope of the signal shape is not maintained here. This is also called sampling, but this is improper sampling. The quality is not maintained here. So this is how we should not do sampling. This is how we should not do sampling, because this is not maintaining the quality. Okay. So this kind of sampling is fine, perfectly fine for us. Okay, right. There is one more way of sampling. There is one more way of sampling, and what is that way? Let me show you. One more way also we can sample, and that is collecting more samples than required. See this one? Same signal. The envelope of the signal is maintained. So here, compared to this one, we are collecting double the number of samples. Is the quality maintained? Yes, perfectly yes. We are collecting more samples. Is that an advantage or a disadvantage? Compared to these two, which one is more advantageous? Sir, more samples, I'm more happy. No, it's not more samples means it's not more money, okay? More samples is not more money, okay? So more samples means we have to use more storage, na? For getting the same quality, here, let's say there are 5 samples here. Instead of 5 samples, there are 10 samples here. If you take this, if you store these samples or these samples, when you retrieve this also you get this signal. When you retrieve this also you get this signal. Which one is easier to store? Which one takes less memory to store? This one takes less memory. So collecting too many samples is not advantageous, it's disadvantageous. Collecting less number of samples will lose quality. Collecting many more samples will waste our storage, or when you are communicating also it will increase our bitrate, which will increase our bandwidth requirement. So collecting samples very huge compared to our requirement is not useful. Collecting less number of samples than required is also not helpful. Collecting only samples that are necessary, that is important. The optimum is How many samples is sufficient? Only that many we should collect. Okay, so we should collect optimum number of samples for best performance. And what is that optimum? We'll talk about it. So that is the whole point of discussion. How to sample? We should sample in such a manner that quality should be preserved, quality should not be lost, quality should be preserved, and too many also should not collect, because it will waste our storage. Wonderful. Simple example I'll tell you. Simple examples. When you're chatting, WhatsApp or any other social media platform, you might chat some messages. Any other, you'll chat with many other messages also. I'll take one example. So this one, we generally don't type the whole thing. Many people don't type the whole thing. Some people type it as, some people type it like this. No one will type like this. No one will type like this. Many people will type like this. Many people will type like this also. Is this not sampling? Out of many samples, we are collecting few samples. But how should we sample? We should not sample like this, because sampling like this, we are losing the information. Sampling like this, we are maintaining the information. Sampling like this, also we are maintaining the information, but we are using more letters than minimum required. Both are maintaining the quality. So we should collect a sufficient number of samples. In this case, two letters. We should collect sufficient number of samples to maintain the quality. Okay, whatever is the minimum number of samples that we should be collecting, that is what we call it. That is what is given by sampling theorem. Okay, we can talk about that in detail in other classes. You can search with my name on sampling. On sampling, I've taken wonderful videos on YouTube in detail also. So that's why I'm not getting into the depth of sampling here. You can search through YouTube, you'll get some videos, wonderful videos. Right, so I'm giving you a brief idea of sampling here. So this is also sampling. You can compare this way. This is very easy way to understand sampling. We are collecting from many samples, we are collecting few samples. When we are maintaining quality, when we are collecting sufficient number of samples. And what is that sufficient number for sampler? That sufficient number is, for message signal m of t, there is one parameter that is important while we are sampling, and that is bandwidth. Let me say the bandwidth of the signal is b hertz. Bandwidth of the signal is one parameter that will decide how many samples we should collect, or the sampling rate that we should use. The only parameter that is important in sampler is fs, or sampling rate we call it. Fs means sampling rate. So sampling rate is one very important parameter in sampling. So how many samples should we collect? According to sampling theorem, we should collect at least minimum of 2b number of samples. If you collect these many number of samples, quality will not be lost. In other language, they call it as that loss of quality, losing of quality, they have named it as aliasing effect. They have named it as aliasing effect. I'm not getting into the details of it. But when you satisfy this criteria, when you see this one, fs is greater than or equal to 2b. Sampling rate should be minimum 2b or more than 2b. So the minimum number of samples, similar to this case, what should be the minimum number of samples here? 2b samples for every second. For every 1 second, you should collect 2b number of samples. If b is bandwidth, you should collect minimum 2b, or more than that also is also fine. So 2b number of samples per second is the minimum number of samples we should collect. Anything more than that is perfectly fine. Less than that, we are going to lose quality, and that losing of quality is what we are calling it as aliasing effect. We are calling it as aliasing effect. So when you satisfy this criteria, we don't have this aliasing effect. And there is one more thing also that is important here. Whatever sampling that we do practically is not ideal sampling. We don't do ideal sampling, we do practical sampling, or flat top sampling we call it. So practically we use only this one, flat top sampling. When we use this flat top sampling, we use rectangular pulses, we don't use impulses. When you are using ideal sampling, we use impulses, but we don't have practical impulses. So that's why ideal sampling is not practically possible. But whatever mathematical analysis that we do in ideal sampling, whatever understanding that we get there, that will help you to understand flat top sampling also, or practical sampling also, and other sampling, natural sampling also. So the mathematical understanding that we have in ideal sampling is wonderful. That will help you to solve a lot of questions. But what we use practically is not ideal sampling, we use practical flat top sampling or practical sampling. The other name for flat top sampling is practical sampling. In flat top sampling, we use, instead of impulses, we use rectangular pulses like this. We use rectangular pulses like this. When you use rectangular pulses like this, whatever is the width of the rectangular pulses, let me say the width is tau, that width is also very, very important. That width is also very, very important. Too much bigger width is not healthy. Okay, so in my other YouTube videos, I have derived the condition. I have explained very clearly the condition for that width of the pulse also. But in today's session, I'm just going to write the condition. Width of this pulse should be less than or equal to TS. TS means sampling time. When you get sampling rate, inverse of this will give you sampling time. So 1/10 of sampling time or less than that should be the width. Whatever is the sampling gap, whatever is this gap, right? In this gap, 1/10 of it, that should be the width, or less than 1/10 is also fine for us. To maintain the quality, this criteria also should be satisfied. If this criteria is satisfied, if this criteria is not satisfied, we are going to have quality issues. And what is that? What is the name of that quality issue? We call it as aperture effect. We call it as aperture effect. And if you don't want to have loss of quality because of aperture effect, you have to satisfy this condition. When you satisfy this condition, we will not have aperture effect. When we are using sampling, specifically flat top sampling, there are two issues for us. One is aliasing effect and aperture effect. Second one is aperture effect. These are the two effects which will impact the quality of sampling. So if we don't want to have quality reduction, if we don't want to have aliasing effect as well as aperture effect, what we have to do? We have to satisfy these two conditions. This condition for no aliasing effect and this condition for no aperture effect. So that is the broad understanding of sampler block. Okay. So let us get into the next block. Okay, next block is quantizer. There is a lot to discuss about this quantizer. So definitely I'll discuss the basic idea first, and I'll be going little deeper also, because whatever problems I'm going to discuss in tomorrow's session, the complicated questions definitely are based on quantizer. When they're talking about PCM system, generally they ask question on signal to quantization noise ratio. Without a little bit of depth in quantizer, you'll not be able to solve those questions. So that's why I'm going to go into decent depth in quantizer. I can't cover complete depth of quantizer, but I'll give you a pretty good idea about quantizer so that we'll be able to solve any question on pulse code modulation. Right, quantizer. First, let us understand what is the basic idea of quantizer. Why do we need this quantizer? First of all, let us try to understand. So, after quantizer, just try to understand. We are trying to understand why we need quantizer, right? We are trying to understand why we need quantizer. So after quantizer, what is that block? The block after quantizer is encoder. And the block before quantizer is sampler. So we know what we have here. We have just now discussed what is happening here. There is a signal m of t here, something like this. Let me say the highest voltage is something like 4 volts. Okay, as a function of time. Now, after sampler, we know how the samples will look like. The output of sampler, we know how it looks like roughly, something like this, as a function of NTS. So what we have here is m of NTS, and we know the criteria that we should be satisfying here. Fs should be greater than or equal to 2b, and tau should be less than or equal to Ts by 10. That is the condition that we should satisfy while designing a sampler block. Right. So we are having samples. So the samples here are taking 0 to 4 volts. 0 to 4 volts. So what voltage these samples will take? These also will take voltages from 0 to 4. What particular voltages they will take? That we don't know, right? It can be any voltage from 0 to 4, no? So how many samples are there? A lot of samples are there. Each sample will take any voltage from 0 to 4, but we don't know exactly which voltage it takes. So how many possibilities are there here? For each sample, what are the possibilities? From 0 to 4, any voltage is possible here. So how many possibilities are there? Infinite possibilities. I'm not saying infinite samples are there. Infinite samples are not there. Finite samples are there. We have converted infinite samples to finite samples. But how many amplitudes are possible here? Here also infinite amplitudes are from 0 to 4. How many real numbers are there? Infinite are there, no? Which means infinite amplitudes are possible. Same signal when it is sampled, sir, we are getting finite samples, no? Finite samples will have finite amplitudes only, no? But yes, correct, finite amplitudes only. But what are those amplitudes? That we don't know, no? It can be any other. Those finite samples will have finite amplitudes only, but we don't know exactly what voltage these samples will take. But that can be anything from 0 to 4. From 0 to 4, how many number of voltages are possible? 0 to 4, there are infinite set of voltages possible. From that set, these samples will take one of those set of infinite samples, infinite voltages. Right. So what are the possibilities here? Finite samples will take finite voltages only, but the set of voltages possible here are infinite. If you take some voltage, let's say this sample, what voltage will it take? It can take some voltage which is close to like 1.1 or 1.2, but what is that exact voltage? We don't know, right? So it is one of the voltage from 0 to 4. From 0 to 4, there are infinite possibilities. So from that infinite possibility, one possibility it will take, one possibility this will take. So totally infinite amplitudes are possible. I'm not saying all the infinite amplitudes will be taken by these samples, no. But among those infinite possibilities, these will take some possibilities. But we don't know what those possibilities are. So we should be capable of converting this infinite possible amplitudes into bits. What is our final agenda? Our agenda of PCM system is to convert into bits. We want ones and zeros. We want to convert into bits, right? So if you want to convert into bits, if you want to convert infinite samples into bits, how many bits are required? Try to understand the relation between m possibilities or m voltages, you can say. M possibilities, if you want to convert into bits, the number of bits required is log m to the base 2. That is the general formula. I'll just give you simple things. If it is two possibilities, if you want to name two things using bits, how many bits are required? Tell me. There are two things. Let's say two things. I want to name this one and I want to name this one using bits. How many bits are required? One bit is sufficient, no? I can name this as 0, I can name this as 1. Sufficient, no? If there are two possibilities, one bit is sufficient to name them or differentiate them. So one bit is sufficient here, right? So how about four possibilities? If there are four things, if you want to name them four differently, how many bits are required? Two bits are sufficient, no? 0, 0, 0, 1, 1, 0, 1, 1. We can create four possibilities using 2 bits, right? Similarly, how about m possibilities? Is this formula okay? Log m to the base 2. How about infinite possibilities? If there are infinite possibilities, we need infinite bits. So if you're trying to convert these samples into bits using an encoder, try to understand. Without quantizer, if you're trying to convert into bits, we need infinite bits. Is it possible to use infinite bits? Not at all possible, because if you're using infinite bits, we need infinite bandwidth, infinite storage, which is not at all possible, right? So without using quantizer, if you want to convert analog signal to digital signal, we need infinite bits, which is not possible. So what should we do? Infinite bits is not practically possible. What is practically possible? Finite bits. So we want finite bits. Instead of infinite, we want finite bits, something like this. If you want finite bits, we should have finite possibilities. At the input of encoder, we don't want infinite possibilities because we can't spend infinite bits. If you want finite bits here, we should have finite amplitudes possible here. But what we are having here is infinite possibilities. Now you can tell me, what is the job of a quantizer? The job of a quantizer is to convert infinite possibilities, infinite possible amplitudes to finite possible amplitudes. The job of a quantizer is to convert infinite possible amplitudes to finite possible amplitudes. Okay. For example, so the job of a quantizer is to convert infinite amplitudes or infinite possibilities or infinite possible amplitudes to finite possible amplitudes. Finite possible amplitudes. Okay. So that is the job of a quantizer, because once we get finite amplitudes, finite possibilities, once we get finite possibilities, we get finite bits. We can use finite bits to represent an analog signal with bits. Okay. So without quantizer, we can't do analog to digital conversion. We need sampler, we need quantizer, we need encoder. Okay. Right. So just for example's sake, let me take some voltages here. Let me say this is 2.1 and this is 3.9. And let me say this is 2.2 and this is 1.1. Let me say the quantization levels that this quantizer will take. We want to convert infinite amplitudes to finite, right? So infinite means there are all the set from 0 to 4, all the real numbers from 0 to 4. That they are the possibilities here. We want to convert them to finite. No, what are those finite values? That depends on how we design the quantizer. Okay, design of quantizer is a separate topic, so we'll not get into the details of it. Design, if once you have designed the quantizer, you'll know what are those finite amplitudes. We call them as quantization levels. Let me assume the quantization levels here are 1, 2, 3 and 4. Let me assume I've designed a quantizer in such a manner that the quantization levels used here are, for this quantizer design, are 1, 2, 3, 4. Which means at the output here, there are finite amplitudes. No, what are those finite amplitudes? They are nothing but quantization levels. Let me say, for example, the design for this quantizer is in such a manner that the quantization levels are 1, 2, 3 and 4. If that is the case, then, so let us quantize them. 2.1 is quantized and it becomes 2. And 3.9, what is the closest voltage? 4 is the closest voltage. And 2.2, the closest voltage is 2 again. And 1.1, the closest voltage is 1. We are gonna, quantization means it's nothing but approximating the voltages with the closest quantization levels, because we want to convert infinite things to finite things. When we are converting infinite things to finite things, is there anything that is happening which we don't want to happen? Is there something happening because of quantization that we don't want to happen? Something is happening, right? 2.1 is becoming 2. The original voltage in the signal is 2.1 and that is becoming 2. Is there loss of information or not? Yes, there is loss of information. Sir, can we do quantization without loss of information? Not possible. Okay, how can you convert infinite samples to finite infinite possibilities to finite possibilities without some sacrifice? We are getting that advantage. We are getting the advantage of converting infinite to finite only by sacrificing little bit of quality. And that quality we call it as quantization noise or quantization error. Okay. Bruce will talk about it later. Okay. Keep the questions aside. Listen to the concept carefully. Okay. If you just keep your questions aside, you can ask me at the end. Okay. Fine. So when the process of quantization, we are having some problem called quantization error, and that reduces the quality of the signal. So is there any way in which we can overcome it? We can't eliminate this quantization error, because when we do quantization, we are converting infinite to finite possibilities. When we do that, we are going to get some error. We can't eliminate it, but we can minimize it. We can minimize it. How much we can minimize? We can minimize it to any extent. Instead of 4 voltages, if we take 40 voltages, or if we take 400 voltages, then instead of 2, it will become 2.11, something like that. The error, 2.1 to 2, there is some decent error. If you increase more number of voltages here, if you increase more number of quantization levels here, then the quantization levels will be very, very close. Instead of 1, 2, 3, 4, it will be like 0.1, 0.2, 0.3, 0.4, something like that. The quantization levels are close means the approximation also will be closer. The error will be very less. Okay, we can reduce the error. Eliminating the error is not possible. When you are using quantizer, quantization error will be there. But what we can do, what the best we can do is minimize it. Okay. How to minimize it? By using more number of quantization levels. If you are using more number of quantization levels, here how many are there? 4 possibilities, 4 quantization levels are there, 4 amplitudes are possible here. The finite value is 4 here. If you are using 4, how many bits are required? 2 bits are required. Based on the number of bits, number of bits will decide the number of possibilities that it can convert into bits, or the number of finite amplitudes possible here, or the number of quantization levels here. The quantization levels used in Quantizer, or the Quantizer design, is based on how many bits we use in the encoder. If it is an n-bit encoder, the number of bits that we are using for encoding is n bits. What that means is one sample is converted into n bits. This n can be anything, 4, 5, 6, 7, 8 also. In practical, we use n as 8 in PCM system. In practical PCM system, we use n as 8 bits, which means every sample, once you get a first sample, you'll convert that is converted to 8 bits. Second sample is also converted into 8 bits. That is the meaning of 8-bit encoder. 8-bit encoder, what does it do? Whenever it gets a sample, it converts into 8 bits. Every sample, it converts into 8 bits. That is the job of an encoder. Once we know how many bits are being used in encoder, we'll know how many levels it can convert. Once we know how many levels it can convert, we know how many quantization levels should be designed. In the quantizer design, how many quantization levels should be selected, that is decided by the number of bits. Number of bits will decide the quantizer design. Very important. If we use more bits, we can have more quantization levels. When we have more quantization levels, we have less error. So more number of bits is deciding the quality here. Number of bits is deciding the quantization error here. More bits, more quantization levels, and more quantization levels means they'll be closer. If they are closer, error will be smaller. So quantization error is related to number of bits. So if you use more bits, then quantization error will be less. Sir, I will use 1000 bits, sir. Come on, if you use 1000 bits, then data will become very large. For a simple signal, if you are using 8 bits, you'll get some rate x. Instead of 8 bits, if you are using 80 bits, instead of rate x, you are getting 10x rate. Which means instead of sending x data, you are trying to send 10x data for conveying the same information, which is useless. Okay, my voice, I've spoken here, and I got some 1 MB of data here. If you are using 8 bits, you are getting 1 MB of data. I have spoken for 1 minute, you have recorded, you have converted into bits, you got 1 MB of data. Okay, instead of 8 bits, if you are using 80 bits, my same signal will come here, but instead of 1 MB, you'll get 10 MB. Same voice. No increase in quality because of using 10 MB. Not huge increase in quality will not be there. Okay, there is no point of using 10 MB where you can use only 1 MB. Okay, so increasing n as you want so that you can reduce quantization error is not advisable. N, if it is less, more quantization error will be there, quality gets impacted. More n, yes, quantization error, quality because of quantization error will be very less. The quality reduction because of quantization error will be very less when n is large. But because of, just to reduce just to get superb quality because of quantization error, or just to avoid quality reduction because of quantization error, if you try to increase too much n, that will increase bit rate or bandwidth, which we can't afford. So that's why too much of n is not good for us. Too small a n is also not good for us. Too small n will give us bad quality in terms of quantization error. Too big n will impact the bandwidth. So that's why we should choose an optimum value of n. We should choose an optimum value of n, okay, which will balance the quality, which means the quantization error, as well as the bit rate and bandwidth. Okay. Wonderful. Very interesting concept, right? So that is the idea of quantizer. Right. So there is more to discuss on quantization. There is actually more to discuss on quantization. Okay. So before talking more about quantization, let me conclude the rough idea of PCM system. Then I'll talk more about quantizer in detail. Okay. Right. So we have already talked about encoder in the previous slide. What does encoder do? It converts samples, the quantized samples. It converts quantized samples. Right. So M of NTS, what we have here? we are having same samples, but after approximation with some error, we are having the same samples. Same locations we are having samples, same locations, almost same samples. As you increase the, practically we don't use only 4 quantization levels, practically we use 256 levels. So error will be very, very small. So these samples are approximated to some values here. So generally quantization, what will it do? It approximates these samples to some other closest samples, because the error practically will be very small. So generally quantization will do some kind of approximation, you can say, approximation to the closest quantization level. So that's why I'm denoting it as m cap of NTS, which is like a slightly modified version of m of NTS. Right. So that m of NTS, yeah, that m cap of NTS that is applied as input to the quantizer. Here we are having samples only, quantized samples we are having quantized samples. These samples, when you pass through encoder, when the first sample is given, it will convert it into 8 bits. When the second sample is given, that is also converted into 8 bits. Third sample is given, that is also converted into 8 bits if it is a 8-bit encoder. Generally, in a general manner, we take it as n-bit encoder, because n can be any value. In a practical PCM system, they use it as 8. Fine. So every sample is being converted into bits. This sample is converted into bits. One zero one 0 0 1 1. And second sample, when the encoder gets the second sample, that is also being converted into again 8 bits. Something like that. Next sample is also converted into 8 bits. That is how it happens. The job of an encoder is to convert every sample that is given to the encoder into bits. So when a sample is given to encoder, that is encoder is converting into bits. Right. So one sample is converted into n bits. So the only parameter that is important in encoder is value n, the number of bits used for converting a sample into bits. Right. So now let us talk about the whole thing, the pulse code modulation as a whole. Okay. Right. So let me revise everything here. We are having m of t here. Once you sample, you are getting sampled version of m of t, which is m of NTS. And once you quantize, you are getting m cap of NTS. We are getting m cap of NTS. And after encoder, we are getting bits. Right. So regarding sampler, we have talked about in decent detail. So the criteria for sampler is fs should be greater than or equal to 2b. Fs should be greater than or equal to 2b. And the other criteria is tau should be less than or equal to Ts by 10. So I have told you in the previous slides what happens when you satisfy this criteria. When you satisfy the first criteria, aliasing effect can be avoided. And when you satisfy the second criteria, when you design the sampler, when you satisfy the second criteria, aperture effect can be avoided. Okay. So these two conditions should be satisfied. So this has infinite samples and this has finite samples. And how many are those finite samples? It is fs number of samples for every second. In 1 second duration, we are going to collect fs samples. How much time you send the signal? Let's say if you are using the signal, if let's say I have spoken for 10 seconds. For every second I am taking 10 fs samples. For 10 seconds I will be using 10 fs samples. So if I am spoken for 10 seconds here, I am going to collect 10 times fs number of samples. How much time the signal is there? Those many times fs. Let's say 100 seconds, then 100 fs samples will be collected here. So we are going to collect fs samples every second. Shivam, you are asking something. How can I check which sample is optimum? What do you mean by that? Optimum sampling rate? Is that what you mean? Okay. So these fs number of samples per second, once you quantize, when you quantize, will the number of samples increase or decrease, or will they remain same? One sample is given to quantizer. What does it do? It does some approximation, it does some quantization, and it will give you as output. One sample given, one sample is given as output. Quantizer will not eat away samples, right? Every sample that is given to the quantizer will approximate it and give it as output. So any sample given to quantizer, it will give it as output by approximation. So how many samples you are giving to quantizer, same number of samples will come as output. So the number of samples coming as output of quantizer is fs number of samples per second, same number of samples. Now let us talk about encoder here. We know what an encoder does. What does encoder do? One sample it will convert into n bits. This is what it does. But how many samples we have? Let's say we are having fs number of samples, fs samples. Fs samples will be one sample is converted to n bits, means fs number of samples is converted into n into fs number of bits. But we don't have fs number of samples. We are having fs samples every second. So if you are having fs number of samples per second, we are going to have n into fs number of bits every second. So at the output of encoder, these fs number of samples are being converted into n into fs number of bits every second. So the parameter that is important at the output of encoder or at the output of PCM system, what is that? It is bit rate. We denote it as RB. R means rate, B means bits. And what is the bit rate? Just now we got it. Rate means how many you are having per every second. For every second, how many you are having. So if it is bit rate, how many bits are we having per second? Per second, how many bits are we getting at the output of encoder? Fs samples per second are converted into NFS bits per second. So the bit rate is n times fs bits per second. N times fs bits per second. That is the bit rate. So for a PCM system, it is converting analog signal into bits. How many bits are we having is decided by how many bits are we using in encoder design and how much sampling rate are we using. And what does sampling rate depend on? Sampling rate depends on bandwidth of the signal. So finally, analog to digital conversion depends on two parameters. One is the bandwidth of the signal that we are using, and obviously because of bandwidth, sampling rate is decided. And second thing is how many bits we are using for encoding. How many bits we'll choose it based on how much quality we want based on quantizer. Based on quantization error, how much quality reduction is okay for us. Based on that, we are going to select an optimum value of n. Okay. Right. Shivam, I did not get your question. Can you ask again in a different way? Right. So let me give you more broader view. Once we get bits, what happens next? You'll understand a broad view of what happens in communication, in digital communication especially. Try to understand carefully. The next stage after PCM, you can say. After PCM, what happens? Here you are having analog signal m of t, and here we are having bits. Here we are having ones and zeros. Okay. So these ones and zeros, what is the next step? Once we get bits, do you think these bits can travel through the wires, either optical fiber cable or electrical cable, any cable? These cables are not capable of carrying the numbers, the digits that we talk about. The wires are not capable of carrying the digits. If you talk about any electrical wire, any coaxial cable or twisted pair cable or any electrical cable also, they carry only electricity, right? So they are capable of carrying only electricity. Okay, we can't send ones and zeros. By writing ones and zeros, we can't send anything through the wire. Okay, electrical wires are capable of carrying only electricity. We should convert whatever information we want to transmit. We should convert that information into electrical format. Otherwise, we can't communicate. Okay, these bits can't be communicated without conversion into electrical pulses. Okay, when you're talking about optical fiber cable, you have to convert into light pulses. Okay, we have to do some kind of conversion. Otherwise, we can't put it into the channel. So once you do analog to digital conversion, we can store these bits in our memory, in our hard disks or in our some memory devices. We can store these bits in the form of voltages only. There also we store as voltages only. It's not like ones and zeros. It's not like ones and zeros written. You know the flip-flop concept, right? Flip-flop. Some voltage will be treated as 1 and some other voltage is treated as 0. Right? Say that time again. Half an hour. Okay. Right. So even in the memory also we store bits as voltages only, because that is how we store them. If we want to communicate also, we're gonna convert these bits into voltages only, because electrical voltages are a convenient way for us to communicate or store. Okay. Just for analysis, we write them as ones and zeros here, but internally when it is storing or communicating, we can't store it in as it is numbers format. Okay, we have to convert these ones and zeros also into voltages while we are communicating or we are storing, when we are storing. Okay, so what happens next? We use some kind of binary signaling scheme. To convert these bits into voltages. So binary signaling schemes, what are they? So there are some schemes called NRZ, non-written zero scheme, a written zero scheme, and then Manchester coding scheme, on-off signaling scheme, and alternate mark inversion. These are the basic techniques that we use. There are highly advanced techniques also, but these are the techniques that are being discussed in our textbooks. So you can use one of these techniques to convert bits into voltages. So for example, let me take non-written zero technique. If you are using non-written zero technique, what does it do? It converts one bit into a positive voltage and 0 bit into a negative voltage. That is how this will do. It converts bits into electrical pulses. So is it differentiating or not? 1 it is converting into some positive rectangle, and 0 it is converting into some negative rectangle. Is it differentiating or not? When you transmit this through some wire or some wireless communication system, what happens is at the receiver, when you receive some kind of positive rectangle, you'll understand that okay, 1 is being transmitted. When you receive a negative rectangle, you'll understand that okay, 0 might be transmitted. So once you see these pulses, you'll note them as okay, at the receiver you'll note them as okay, 1 is received, 0 is received, 1 is received, 0 is received. Like that you understand, at the receiver you'll understand what bits are being received. Once you know what bits are being received, those bits you know how to convert a digital signal to analog signal. You can use digital to analog converters. Once you receive bits correctly, these bits you can use using digital to analog converters. You can convert those bits into analog signal finally. From these bits, by using these pulses, we can get the bits back at the receiver, and by using these bits, you can convert into original analog signal using digital to analog converter. What is the next stage? Okay, is this the final thing? Okay, we can transmit this. We can comfortably transmit this, but this is not the only thing that we do. We do one more thing also. Marty will talk about quantizer design also little bit in the next slides. Okay. Okay. Next block is pulse shaping. Practically we use this block also. So what we have here is something like this, rectangle pulses like this, and each pulse can take a time of TB seconds because we are converting every bit, ones and zeros. Every bit is being converted into rectangular pulses. So each rectangle pulse can occupy a duration of TB seconds, 1 bit duration. Okay. So the bandwidth of this signal. So this signal does not have any concept called bandwidth. Numbers does not have anything called bandwidth. Only electrical signals. The signals will have bandwidth. Okay. Bandwidth is a concept of frequency. It makes sense to talk about frequency only for signals, right? So for a signal, for example, electrical signal, we'll have a concept of frequency, and we can talk about bandwidth for this. So if you want to talk about bandwidth, you have to find Fourier transform. So if you find the Fourier transform of rectangle pulse, it will be sinc function, and using that sinc function, you can find the bandwidth of this rectangle pulse. And the bandwidth of rectangle pulse will be, if you know for Fourier transforms, find the Fourier transform of this rectangle pulse, you'll get a sinc function with a null point at 1 by TB, which is RB, bit rate. So bandwidth of this rectangle pulse is RB. Okay, right. So why do we do pulse shaping? We do pulse shaping for multiple reasons. One reason is to reduce the bandwidth. Can we reduce the bandwidth or not? See, here we are using rectangle pulses. For 1 we are using one shape, for 0 we are using some other shape. Some other little slightly different shape. We are trying to differentiate 1 and 0 using different shapes. Why should we use only rectangle shapes? Why can't we use some other shapes? Yes, we can use definitely. Only thing is at the receiver, by looking at that shape, you should be able to say, okay, 1 is received or 0 is received. You should differentiate only that much. Okay, for example, I'm having this and I'm having a bottle. I want to communicate. Okay, so there is one person in the next room. Okay, and there was one boy who is helping me. I am treating this as 1. I am treating this as 0. The person in the other room also, I'll tell him that if I send a bottle, it means 1. If I send this pen, it is 0. Now my helper came and I sent the bottle. After seeing the bottle, the person in the other room, will he understand it as 1 or not? Forget about rectangle pulses. If I send bottle also, if I send the pen also, if you have some understanding mechanism. What is the understanding mechanism here? Positive rectangle means 1, negative rectangle means 0. This is the technique that we use in non-return 0. In return 0, we use some other technique. In on-off, we use some other technique. You are using different things to represent 1 and 0 in different techniques. Okay. So if I send a bottle to the other room, he will understand that, okay, 1 is transmitted. If I send a pen, he will understand it as 0 is transmitted. So we can use any two different shapes or any two different things, not only shapes, any two different things to differentiate 1 and 0. Okay, right. So don't think that only rectangle shape should be used. Definitely rectangle shape can be used, but it's not those are not the only shapes that can be used. We can use other shapes also, but care should be taken while we are designing the shapes. It's not like any shape we can use. It's not like that. It will create some other problems. It will create some other problems called intersymbol interference. The problem created by whatever, if we want to use whatever shape we want, then it will create problems called intersymbol interference. If you don't want that problem, we have to use properly designed shapes, and that is pulse shaping. There are multiple pulse shaping techniques, and the mostly used pulse shaping technique is raised cosine pulse shaping technique. Raised cosine pulse shaping technique. This technique will design the pulse shape that is being used properly, so that two things are being done. We can reduce the bandwidth, and we can also avoid intersymbol interference. Sir, what is meant by intersymbol interference? See this one, this rectangle pulse. If you try to send this rectangle pulse through a channel, what happens? Will the shape change or not? Rectangle pulse cannot retain its shape because rectangle pulse Fourier transform is sinc function. Sinc function has infinite frequencies. When you pass through any band limited channel, a wires are always band limited only. They can only transmit only certain frequencies. They can't transmit infinite frequencies. So when you transmit a signal with infinite frequencies, that wire will cut off some frequencies. At the end of the wire, some kind of frequencies are cut off, which means you don't have an exact sinc function in frequency domain, which means you don't have the exact rectangle shape. So what happens is rectangle shape will become smoother shape because some frequencies are cut off. So what happens, this shape will interfere with this shape and this shape will interfere with this shape. One symbol is interfering with another one. So that is what we call as intersymbol interference. So to avoid this intersymbol interference, when we transmit through band limited channels, we have to take the help of pulse shaping. So practically we definitely use pulse shaping. Practically we use pulse shaping. For wireless communication it is compulsory. For wired also mostly we use pulse shaping, because pulse shaping helps to maintain the quality. It helps us to avoid ISA problem. Right. So pulse shaping, what will it do? It converts this pulse into some smooth pulse, some smooth shaped pulse, something like this. Sir, it is interfering now already. Yes, it is calculated interference. So the next one is something like this. Something like this. It looks like first pulse is interfering the second one, but care is taken. While we design this, care is taken in such a manner that one pulse looks like interfering with the next pulse, but it is not interfering at the required instance of time. See this one? When you're talking about the first pulse, we sample at this place, we get positive sample, okay, we understand it as 1 bit. We sample at this instant, if you get negative sample, yes, we understand it as 0 sample. We are not interested in all the time, we are interested only at particular times. We're going to sample at particular times, and we are going to understand what kind of sample we have transmitted, or we are trying to understand the bit at a certain instance of time only. So means this is a tricky concept. So my YouTube videos are also available based on this concept. You can go through them. I have taken 2 hours of session based on this pulse shaping concept. Wonderful concept, my favorite concept you can say. And in YouTube you will not get that concept in detail the way I have dealt it in YouTube. Right? You can go through it if you are interested. It is very important for GATE. Multiple times questions were being asked. Right. So for here I am giving you the rough idea here. So when you use smooth pulse, smooth shape, what happens? Rectangle is a sudden change. Sudden change means, sudden change always represents faster change. Faster change means high frequency. So that's why this will have higher frequencies, which means higher bandwidth. So because of pulse shaping, because of smooth shape, bandwidth can be reduced. And what is the bandwidth? At the output of pulse shaping, what is the bandwidth? The bandwidth is, it is 1 plus alpha divided by 2. Whatever is the bandwidth before pulse shaping, whatever signal you apply to the pulse shaping circuit. If the bandwidth is A, it will be 1 plus alpha by 2 into A. If the bandwidth is RB, it will be 1 plus alpha by 2 into RB. Whatever is the bandwidth before pulse shaping circuit, the bandwidth will get multiplied with 1 plus alpha by 2. Okay. Because of pulse shaping, bandwidth gets multiplied with 1 plus alpha by 2 factor. And what is this alpha? Alpha is roll off. We call it as roll off factor. What is the significance of roll off factor? I've discussed in detail about this topic in my other videos, but right now I'm just giving you a brief view of what is this alpha. Alpha, we call it as roll off factor. What that indicates is how smoother you are shaping this pulse. If you are doing it more smoother, then more smoother means low frequency will be present, bandwidth will become smaller. Which means small value of alpha means we are doing more smoother shape, we are using more smoother shape. Bigger value of alpha means it's not a very smooth shape, you can say, but definitely smoother than rectangle pulse. So alpha value, we call it as roll off factor. Roll off factor. And alpha ranges from 0 to 1. When alpha equal to 0, we get the minimum bandwidth possible. We get the minimum bandwidth possible. And what is the minimum bandwidth possible? It is RB by 2. If the bandwidth at the input of pulse shaping circuit is RB, we can reduce the bandwidth by 2 times. We can reduce the bandwidth by 2 times by using pulse shaping circuit. We can reduce the bandwidth by 2 times. That is the minimum bandwidth possible. And what is the maximum bandwidth possible at the output of pulse shaping circuit? It is RB only. If you put alpha equal to 1, we are getting RB, which is same as the input bandwidth. If the rectangle is having a bandwidth of RB, we are going to get this kind of smooth shape with a bandwidth of RB again. Sir, the shape is different now, bandwidth, is it not reduced? But in this case, it is not reduced. If I need alpha equal to 1, yes, we are using some kind of shape like this, but its bandwidth is same as rectangle bandwidth. Sir, what is the advantage? Yes, we are not getting the bandwidth reduced, but we are getting the advantage of ISA reduction. There are 2 reasons why we are using pulse shaping. Main reason is ISI only, not bandwidth. Main reason is ISI. The second reason is bandwidth. When you use alpha equal to 1, bandwidth is not getting reduced, but intersymbol interference will get reduced. Okay. Right. So whenever they use minimum bandwidth, whenever they use the concept of minimum bandwidth, whatever is given to pulse shaping circuit, half of it will be the minimum bandwidth. Which is RB by 2 in this case. Maximum bandwidth, when they say, okay, it can with pulse shaping also maximum bandwidth is RB, or when they say just bandwidth. Whenever they say, people say bandwidth, when they ask the question of bandwidth, just bandwidth, they don't say minimum or maximum. When they say maximum, we are very clear. When they say minimum, it is very clear. Many times in digital communication, the confusion is about whether they are talking about minimum bandwidth or maximum bandwidth. When they simply use the word bandwidth without mentioning maximum or minimum, that is when confusion arises. In those kind of cases, you have to be very careful. So what should you do? When they simply use the word bandwidth, what should you keep in mind? You should keep in mind that, okay, they are not doing pulse shaping, they are just using rectangle pulses. Keep that in mind. If they don't use the word maximum or minimum, if they are using maximum or minimum, okay, they are doing pulse shaping, we know maximum bandwidth and minimum bandwidth. If they are not doing pulse shaping, then only they will ask the word bandwidth. When they use the word bandwidth only, not maximum or they don't mention the word maximum or minimum, then I assume that, okay, they are using only rectangle pulses to transmit. They are not using any pulse shaping. If they are using rectangle pulses, we know what is the bandwidth, which is same as maximum bandwidth when you are using pulse shaping. Maximum bandwidth, what we get when you are using pulse shaping, or bandwidth when you are using rectangle pulses, both are same. Which means when they don't mention the word bandwidth, okay, think of it as maximum bandwidth only. Okay. Wonderful. I hope it is clear till this point. Fine. So with that, I've covered the broader idea of pulse code modulation. Okay, I've covered the broader idea of pulse code modulation. So if you are interested, I'll discuss a little bit more about quantization. Shall we discuss? Are you interested? Yes, no? If you are interested to listen, I'll talk about Quantizer also in little bit more detail. For the next 15 or 20 minutes, I'll talk about Quantizer. I'll explain few parameters on Quantizer so that it will help you to solve the questions in tomorrow's session very easily. Okay. Guys, if you have not subscribed to the channel, please subscribe, and if you like this session, please like the video. Okay, and also comment. If you want to comment something, you can put the comments in the comment section, not in the live chat, in the comment section. Okay, and I'll also give you a homework in today's session. Let me show you the homework also. Okay, so I've given you 3 questions, very basic questions I've given. So based on sampling and quantization, very basic questions. So once you solve them, 3 questions I've given. Once you solve 1, 2, 3 questions, once you solve, put the answers in the comment section. I'll check the comments and I'll reply if they are correct or not. I'll give you the answers in the next class also. In tomorrow's session, the first thing that I'll do is I'll give you the answers for these 3 questions. Okay. So don't forget to comment the answers in the comment section, not in the live session. Okay. Fine then. So this is the homework questions. I'll post this PDF, whatever I have written in today's session. I'll be sharing it in our Telegram channel. So if you're not on my Telegram channel, you can join with that channel. Just type my name. You'll get into it. Right. So let's talk about Quantizer for the next 15 or 20 minutes. You have to pay a lot of attention. I'm going to discuss wonderful details here about Quantizer. So let's talk about what is, we have understood what a quantizer does, right? We've understood what a quantizer does. Now try to understand what parameters are there inside the quantizer and what is the idea behind designing a quantizer. Okay. For example, let's say we're designing a metro line. Okay. We're designing a metro line. So this is some okay. So this is metro line from Noida to New Delhi. So let's say I'm an expert in designing things. So government has given me an opportunity to design. Okay, where should be the railway stops and all that. Okay, so putting these stops is also kind of quantization only, because there is a person here. If he wants to get onto the train, if you can come here and ask the train to stop, will the train stop? If the train stops, and if the another person comes here and asks the train to stop, it will stop here also. If it keeps on stopping at every point of time, it will take infinite time to travel to the destination. So stopping at every place is not wise. So that's why we have stations. Okay, instead of taking all places as stops, taking only particular places as stops, that also we can call it as quantization. Infinite possibilities, originally infinite possibilities are there to board that train. If you take all those infinite possibilities, it takes infinite time to travel. Instead of infinite possible stations, if we can convert it into finite possible stations, that also we can call it as quantization. That is exactly the concept of quantization. We are converting infinite possibilities to finite possibilities. There are infinite locations at which people can board the train, but instead of that, I am talking only finite locations, so that it will be train can take least amount of time to reach the destination. Right. So from Noida to New Delhi, let me say the distance is 16 kilometers, for example. Okay, the distance might be different from what points you are selecting in New Delhi and in Noida. Just let me say, for example, 16 kilometers. Now, I am asked to design in such a manner that there are 8 stations, only 8 stations. How many stations we are going to have is similar to, at the output of quantizer, what we are going to have? Quantization levels. Quantization levels is similar to stations here. Okay. So how should we design? Before understanding how to design, let's talk about once we design a station. Let's say we put a station here. A person is there here. What should he do? He should go to the nearest station, right? He should go to the nearest station. Here he can't board the train here. He should go to here or here, whichever is closer. He should go there and board. This distance that he is traveling to board the train, that extra distance he is traveling to board the train, that is what we can think of it as quantization error. If infinite stations are there, then he could have boarded here only. But since infinite stations are not there, he's boarding here, which means he's traveling some extra distance. That we can think of it as similar to quantization error. Because of quantizing the train stations, we're having some kind of their quantization error. Here the walking distance. Okay, if we design the stations properly, this walking distance will be as minimum as possible. If this walking distance is more, or this distance is more to travel, then that is not an optimum design, right? So government, let's say government has asked me to design in such a manner that there are 8 stations. There are 8 stations. Okay. Now if I am permitted to have 8 stations, okay, so how will I design? For minimum error for all people, what I'll do is I'll divide the total distance, total 16 kilometers, into 8 parts. 16 kilometers into 8 parts. Into 8 parts, because 8 stations are allowed. 8 quantization levels are allowed, which is we get 2 volts. If I divide this total thing into 8 parts, we get 2 volts as the basic part. If you divide into 8 parts, each part is of 2 volts. So let's start from 0. This is 2, this is 4, 6, 8, and so on, 10, 12, 14, and 16, something like that. So if I design like this, then any person from here, let's say the midpoint, he has to travel a maximum of 1 kilometer, not more than that. If a person is here, he has to travel half a kilometer, not more than that. So the maximum distance that any person will travel in this design is 1 kilometer. The maximum error possible here is only 1 kilometer. Okay. Instead of voltages, I'm talking about kilometers here. The distance, it is exactly same. Just to make it more understandable, I'm converting into this format. So what are we doing while you are quantizing? We are taking the total length or total range, and we are dividing into how many parts. How many parts are permissible? Those many parts. In our language of quantizer, how many quantization levels are there? Those many parts we can divide. How many quantization levels is decided by the number of bits. So number of bits decides number of quantization levels. Based on number of quantization levels, we divide the total range into those many parts. How many quantization levels are there? Those many parts. And each part, the distance between 2 stations or distance between 2 quantization levels, we call it as step size in our language. We call it as step size. In this case, this is what we call a step size. In Quantizer, there is something called step size. Step size is nothing but distance between 2 train stations or distance between 2 quantization levels, right? So this is the range of length, you can say. In our example, we're talking about signal which is having voltages. That voltage of the signal, the range of voltages possible in the signal, that voltage range or voltage swing, that is what is important for us. That voltage swing, imagine this signal also has a signal which is taking voltages from 0 to 16. If a signal is taking voltage from 0 to 16, and if I'm permitted to use 3 bits, 3 bits means how many quantization levels? 8 quantization levels. A signal which takes voltage from 0 to 16 volts, I want to design a quantizer for that by using 3 bits. 3 bits means 8 quantization levels. Then also I'll analyze in the same way. Okay, 0 to 16 voltages are possible. Okay, I'm permitted to have 8 quantization levels. So I'll divide this 0 to 16 into 8 parts. Each part is 2 volts. Each part is 2 volts. That each part is what we call as step size. We call it as step size. And what are the quantization levels? We're going to select the midpoints of quantization boundaries. See this one? From 0, whatever is the step size, every step size we are selecting one boundary, one quantization boundary. These 0, 2, 4, all these are quantization boundaries. We call them as quantization boundaries. They are not quantization levels, they are quantization boundaries. In this case, the 16 is the total range. And what is the 8 here? Quantization levels, number of quantization levels. Number of quantization levels. Number of quantization levels, which we denote with M. Or some people would denote it as N also. Let me rub this number. Rub this number. Let me generalize this. Whatever we have discussed, let me generalize. So number of quantization levels m, and numerator is voltage swing, the total range of kilometers possible or total range of voltages possible, or voltage swing means highest voltage minus lowest voltage. Peak voltage, positive peak voltage minus negative peak voltage will give us the voltage swing. Voltage swing divided by number of quantization levels. Voltage swing divided by number of quantization levels will give us the step size. Okay, step size. Once you get the step size, we are having quantization boundaries. Every step size, after every 2 volts, you are selecting one voltage, and these voltages are boundaries. And how many boundaries will be there? How many boundaries? How many quantization boundaries will be there? See this one. How many boundaries? Anyone can tell me? Can anyone tell me how many boundaries are there? 0 to 16. How many boundaries are there? There are m plus 1 boundaries. Not just m, but there are m plus 1 boundaries. What is m? Number of quantization levels. I'm not talking about quantization levels. I'm talking about quantization boundaries. Right. So this is the first quantization region. What is the quantization level that we're going to select? 1 volt is selected as quantization level. Next, midpoint of the next step. Midpoint of next quantization region. This is regions. We call them as regions. We call them as quantization regions. Between every 2 quantization boundaries, we have quantization region. So between midpoint of quantization regions, we selected as quantization levels. 1, 3, 5, 7. These are all quantization levels. The midpoint of quantization boundaries, we call them as quantization levels. How many quantization levels? Only m. Quantization boundaries will be 1 extra, because if there are m plus 1 boundaries, that will create only m midpoints, which is number of quantization levels. This is how we design. This is the idea behind quantizer design. Okay. So if you want to plot this as input versus output characteristics, if you want to plot this as input versus output characteristics, we'll plot that in the next slide. For now, in this slide, we'll talk about a few other parameters as well. We talked about step size. How about, can you tell me about quantization error possible? Can you tell me what is the maximum error possible? What is the maximum quantization error possible? Can you tell me? Step size, we denote it as delta. Delta is the notation for step size. We have talked about simple parameters. How many quantization levels? We already know about that. I've talked about voltage swing. Whatever message we want to sample and quantize, that message will take range of voltages, right? That range, we call it as voltage swing. That range is important in the design of quantizer. In the design of quantizer, 2 things are important. One is the number of bits, which will decide the number of quantization levels, and another one is range of voltages taken by the signal, which we call it as voltage swing. Voltage swing and number of quantization levels is deciding the step size. Okay, step size is one very important parameter in quantization. Next, how about maximum error? So if this is the quantization level, if the input is, if the signal is taking 1.9 volts, but the closest voltage possible to that is 1, so quantization will be 1. 1.9 volt, when you pass it through quantizer, it will become 1. The maximum error possible is 0.9 there. But 1.9999, the closest level possible is 1. The maximum error possible is 0.9999, something like 1 volt. 1 is the maximum error possible. In this design, more than 1 volt is not possible. Let me generalize. What is the general value of maximum error possible? If this is the step size, this is delta. This is delta. This is also delta. Step size. This is also delta. Midpoint, we are selecting it as quantization level. So midpoint to the next quantization boundary, that will give you the maximum error possible. Okay. The distance between quantization level and quantization boundary, that will give you the maximum error possible, which is half of the step size. So maximum quantization error is equal to delta by 2, which is half of the step size. Okay. I hope it is clear till this point. Yes. Right. So I have discussed 2 parameters here. Let us talk about few other parameters as well. Okay. So the same characteristics, let me plot it as a diagram. The same characteristics, I'll plot it as a input X, input to the quantizer versus output of the quantizer characteristics. Okay. So the voltages possible are 0 to 16, right? So since 8 quantization levels are possible, 0 to 16 is divided into 8 parts. Each part is of 2 volts. So let me select the quantization boundaries 0, 2, 4, 6, 8, 10, 12, 14 and 16. Okay. Okay. Okay, right, let me write the values 2, 4, 6, 8, 10, 12, 14 and 16. Give me a second. Okay, now the midpoint of these quantization boundaries we selected as quantization level. What is the quantization level for 0 to 2 volts? It is 1 volt. What is the quantization level from 2 to 4? 3 volts. 1 is the quantization level. Whatever we have plotted in the previous diagram, same thing I am plotting as input versus output characteristics. Input is X and output is Y. Right. Next 4 to 6. What is the midpoint? 5 volts. That is the quantization level. Okay. Similarly, midpoint of 6 to 8 is 7. So this is how we draw the characteristics of input versus output. So it is exactly same as what we have discussed in the previous slide. So if you want to plot as input versus output characteristics, you can plot like this. Input we know. So if the input voltage is anywhere in this range, in this region, the quantization level is 1 volt, we know that. So any input voltage applied to the quantizer in this range will be quantized as 1 volt. Any voltage applied in this range will be quantized as 3 volts. Similarly, the other regions also. Okay, right. So I'll talk about quantization error also. Yeah, I had not mentioned that clearly. Vaguely I have told what is quantization error. But what is quantization error? Quantization error is, let me say quantizer is Q, input to the quantizer is sample X and output of the quantizer is sample Y. You are quantizing, you are doing some approximation, right? The difference between the sample given to the quantizer and output of the quantizer. In the previous example, 2.1 volt is given, that is quantized as 2. The difference between 2 and 2.1, that is what we call as quantization error. In a generic manner, input to the quantizer minus output of the quantizer, we call it as quantization error. Quantization error is input to the quantizer minus output of the quantizer. So what is more important for us is the maximum quantization error, which we have discussed, which is equal to half of the step size. Okay. Right. Right. So there are a few more things here regarding quantizer. There are two parameters which we have to discuss, and those two parameters are, okay, so those two parameters are quantization noise power and SQNR, signal to quantization noise ratio. So tomorrow what I'll do is, first thing that I'll do is I'll talk about quantization noise power and signal to quantization noise ratio. Very important parameters, very, very important. So I'll talk about those two parameters in such a manner that there are wonderful tricky questions possible from quantization topic. I'll address all those questions when I'm just talking about quantization noise power and signal to quantization noise ratio. There is definitely a confusion in this quantization noise power and SQNR, because for different signals we have to calculate slightly differently. So what is the general idea which we should keep in mind while solving for questions based on quantization noise power or SQNR? Okay, tomorrow the first thing that I'll do is I'll give you the answers for these questions, and I'll appreciate students who have commented the right answers. And after that, we'll talk about quantization noise power and SQNR. And after that, we'll solve questions based on quantization noise power and SQNR. Okay. So we'll stop at this place today. We'll continue in tomorrow's session. Okay. Good night. Take care. And I want all of you to quickly answer these questions and type in the comments as soon as possible. But don't make mistakes. Cross check your answers and type in the comment section. Okay. Very good. Thank you guys. Good night. Take care. We'll meet again tomorrow, same time, 8 o'clock.